In upcoming videos, I'll be discussing two classes, HashSet and the HashMap, which are based on the hash codes of objects. This can be a confusing topic for new programmers, so I want to spend some extra time explaining it. In a previous video, I showed you an image of an abstract set, which showed chaotically placed elements. Since sets are designed to ensure uniqueness by not allowing duplicates, adding an element requires first checking if it already exists in the set. For large sets, this check can become costly, potentially taking ON time, which is linear in relation to the size of the set, something you might recall from my discussion on Big O notation earlier in the course. One way to reduce this cost is through a technique called hashing. By using hashing, we can distribute elements into different buckets. If we divide the elements into two buckets, and each element can reliably determine its bucket, the lookup time can be roughly halved. Similarly, if we use 4 buckets, the elements are distributed even further, which could reduce the number of comparisons needed in each bucket, improving lookup efficiency. A hashed collection will optimally create a limited set of buckets to provide an even distribution of the objects across the buckets in a full set. A hash code can be any valid integer, so it could be one of 4.2 billion valid numbers. If your collection only contains 100,000 elements, you don't want to back it with a storage mechanism of 4 billion possible placeholders. Additionally, iterating through 100,000 elements sequentially to find a match or duplicate would be inefficient. Instead, a hashing mechanism takes an integer hash code and a capacity declaration that specifies the number of buckets over which to distribute the objects. It then maps the wide range of possible hash codes into a more manageable range of bucket identifiers. Hashed implementations often combine the hash code with other techniques to create an efficient bucketing system that aims to evenly distribute objects, thereby optimizing performance. To understand hashing in Java, it helps to first understand the equality of objects. I've touched on this in previous videos, but now I want to be sure you thoroughly understand this subject because it matters when dealing with any hashed collections. There are two methods on java.util.object that all objects inherit. These are equals and hash code, and I am showing the method signatures from object here. The implementation of equals on object is shown here. It simply returns this equals equals object. Do you remember what equals equals means for objects? It means two variables have the same reference to a single object in memory. Because both references are pointing to the same object, then this is obviously a good equality test. Objects can be considered equal in other instances as well if their attribute values are equal. The string class overrides this method so that it compares all the characters in each string to confirm that two strings are equal. Let's review this in some code as the jumping off point for understanding the hash code. I've created a new project called Hashing for this video. I'll set up a series of string local variables. I'll set A text and B text to the same string literal, so hello in double quotes. I have C text, and that's assigned the result of calling string.join with L as the first argument and HE and LO as the next two arguments. D text is the result of concatenating LLO to the string literal HE. Finally, E text is set to the string literal hello, but all lowercase this time. Now, I'll create a list out of these strings so I can process them more easily. I'll call asList on the java.utils.arrays class, passing it my list of strings. Remember, this takes a variable arguments list, so I can just list all my strings as arguments. Next, I'll print each of these strings out, along with their hash codes. Running this code now to see what we get. I've got 5 strings printed, 4 have the value of hello with a capital H and 1 is hello with a lowercase h. Notice that all 4 of the strings with a capital H return the exact same hash code, but the last one is different. Java doesn't care if these are different objects in memory when it tests the equality of strings using the equals method. It just cares that the characters match in one instance compared to another instance. Now let's create a set of strings. I do that by declaring set as the type and string as the type argument. I will call it my set and assign it a new hash set, and I'll pass my hellos list to the hash set constructor. A hash set is a class that implements the set interface and tracks duplicates by their hash code. Most collections allow the creation of another collection type by passing a different collection to the constructor, as I'm doing here, passing a list to a set, but a set's constructor allows any instance that implements collection to be passed to it. I'll now print out my set, and like a list, I can pass that to a println statement. I'll also print out the size of my set. Running this code now. I get two elements in my set, hello with a capital H and hello with a lowercase h. You can see the number of elements equals 2, even though the list I passed to the constructor had 5 references. Let's loop through the elements and see which string references are actually stored in this set. I will loop through the elements in the set using an enhanced for loop, printing the set value. I'll loop through the strings in the hellos list using a traditional for loop. I'm going to compare the string in the set with the string in the list, and I want to use equals equals here because I'm really interested in whether these instances are the same object in memory. If they're the same reference, I'll print out the index of the element in the list. I'll finish by printing a new line after every set element. Let's see what output we get. I get 3 matches. The first set element, hello with an uppercase H, is the same reference as the first 2 list elements at index 0 and 1. The hello element with lowercase is the last element in the strings list. The hash set will only add new references to its collection if it doesn't find a match in its collection, first using the hash code and then the object's equals method. It uses the hash code to create a bucket identifier to store the new reference. I'll talk about the underlying mechanics of the hash set a bit later. Let me show you what all this looks like conceptually in memory. The code set up 5 string reference variables, but 2 of these referenced the same string object in memory, as shown here with aText and btext, pointing to the same string instance. When I passed the list of 5 strings to the hash set, it added only unique instances to its collection. It locates elements to match by first deriving which bucket to look through based on the hash code. It then compares those elements to the next element to be added with other elements in that bucket using the equals method. Again, I'll talk about how Java implements the hash set shortly. For now, I want you to understand how equality and the hash code go hand in hand when using hashed collections. Let's get back to the code and explore this a bit more. This time I'll create my own class, a playing card called playing card in the dev.lpa package. I'll add 3 fields, suit and face as strings, and an integer I'll call internal hash. I'll generate a constructor, but with only 2 arguments. For the moment, I'll add a statement to set the internal hash field to 1. I'll explain this field shortly. I'll quickly add a toString method. I'll return the face and the suit in place of super.toString. Okay, so that's the playing card class. I'll go back to the main method on the main class and set up a couple of cards, an ace of hearts, a king of clubs, and a queen of spades. I'll again create a list of these, passing the list of cards to the asList method on arrays. I'll print the hash code for each here. Running that code, you can see I get unique hash codes for each. Let's create a set of cards and add the cards one at a time. It will be a set of playing cards called deck, and I'll make it a hash set. I will loop through the cards list, add these cards one at a time. The add method on any collection returns true if the element is successfully added and false if not. Because sets don't allow duplicates, it becomes more important to check if the element you expect to be added really was added. Here I check if I get false back, and if so, I'll print that a duplicate was found. I'm also printing the entire set after this loop to see what's been added to the set. Running this code now. You see that all 3 cards were added to the set. The elements are not guaranteed to be in any order, so you may not see the elements printed in the same order as mine, or in the order you added the elements. Okay, next I want to go back to the playing card class and override both the hash code and the equals method. Instead of returning super.equals in the equals method, which we know just calls the equals method on object, I'll just return true so that all my objects will be equal no matter what. But first I want to print out something from this method so I can see when this method is called. Okay, I'll run the code now. This gives me the same result as before, but it doesn't appear the equals method on playing card was ever executed, because my statement I just added wasn't printed. I want to change the hashcode method here next, and this time I'm just going to return my internal hash field, which is currently just set to 1. Now I'll run the code again. You can see the hash code is 1 for all 3 cards, but as you can also see, the code is calling the equals method during the second and third iteration of the loop, and it indicates it's finding duplicates in both cases. The final result is that it considered every other playing card a duplicate, and so only one card is in the set. The first in our list, the Ace of Hearts, was not considered a duplicate. The only time the equals method is called when adding elements to the hash set is when the hashcode algorithm returns the same bucket identifier, which is true here, for our hashcode equals 1. I will go up and change the internal hash to return an 11 if the suit is hearts, and 12 if it isn't. Let's run this to see how this changes things. You can see the hash code for the Ace of Hearts is 11, but in the other cases it's 12. Where there is a duplicate hash code, the equals method is called, which currently always returns true, so the third element, the Queen of Spades, doesn't get added. Let's delete these 2 overridden methods and instead use IntelliJ's code generation tools to regenerate them. The first time you go into this tool, the template won't show IntelliJ default, so select that as I've done here. We want to use getters, so tick that box. Leave the other checkbox unchecked. Click Next. For fields to be included in equals, ensure only suit and face are selected and click Next. For fields to be included in hashcode, select both fields and Next again. On this screen, you would normally want to check both boxes, but I want to show you the code that is generated if this is not checked. So I will ensure both are deselected here and click Create. Looking at the generated code for the hashcode method, we have these extra tests for null, which we really don't need. So what I'm going to do is undo this with Ctrl-Z and go through the creation of the methods again. Note that this time IntelliJ remembers my template selection and also that I checked the use getters during code generation. I'll click Next. I'll deselect internal hash like last time and click Next. For hashcode, I'll leave both fields selected and click Next. This time for non-null fields, I'll check both. As we know, these won't be null and click Create again. This is as good as any implementations for these methods. Notice that the equals method first checks for equal references because 2 references pointing to the same object is the surest test of equality. Then it compares the result of the getClass methods on both objects, and if they're equal, it will cast the object pass to a playing card. It then checks if the suits are equal. If they are, it will check if the faces are equal. You can see the hashcode implementation that was generated. It starts with the hashcode for the string for the suit. It then uses that, multiplying it by 31, a small prime number, and adding the hashcode for the string, the face string's hashcode. Running this code, you see our set has all 3 cards in it, and the hashcodes for each card are now unique. You don't have to use the generated algorithm as I did here. You could create your own, but your code should stick to the following rules. 1. It should be very fast to compute. 2. It should produce a consistent result each time it's called. For example, you wouldn't want to use a random number generator or a date-time based algorithm that would return a different value each time the method is called. 3. Objects that are considered equal should produce the same hashcode. 4. Values used in the calculation should not be mutable. When implementing the hashcode method, it's common to use a small prime number as a multiplier. Prime numbers are preferred because they help spread out hashcodes more evenly, reducing the chance that different objects will end up with the same hashcode, which is important in data structures like hashmap or hashset. Using a prime number as a multiplier is especially useful if your data might naturally cluster or follow patterns which could otherwise lead to uneven distribution of hashcodes. For example, tools like IntelliJ often use 31 as a multiplier, but other primes like 2937 or 43 work well too. Even some non-prime numbers, like 33, can give good results, though primes are generally better. It's best to avoid small primes like 2, 3, 5 or 7 because many numbers are divisible by them, which could lead to less effective distribution and slower performance in hash-based collections. If you're curious, I encourage you to explore this topic further. For now, remember that when using your own classes in hashed collections, it's important to override both the equals and hash code methods. I'll go over these concepts in more detail in upcoming videos, so you'll have plenty of time to get familiar with them. For those who like to understand how things really work, let me encourage you to do some research on this topic. For the rest of you, remember that if you are using your own classes in hashed collections, you'll want to override both the equals and the hash code methods. I'll be covering this quite a bit over the next couple of videos, so you'll have more time to get exposed to these concepts. Java supports 4 hash collection implementations, which I'll be looking at coming up. These are the hash set, linked hash set, the hash map, and linked hash map. In addition, there's one legacy implementation, the hash table, which I won't be covering, since there are more efficient implementations which replace this legacy class. I'll see you in the next video.